my screen?
Oh, sure.
You agree?
As you wish.
Okay.
Yeah.
Okay.
So, bonjour à tous. Merci d'être là pour ce séminaire du PIMM. Aujourd'hui, nous avons la chance de recevoir Dr Maria Laura de BELLIS, qui est chercheuse à l'université de Chieti-Pescara en Italie. Et now I will switch to English.
Okay.
Thank you very much for accepting to participate in this seminar.
You're welcome.
You will present some work about a new computational method.
Yeah.
So you have about 45 minutes to present, and then there will be some questions. And so feel free to ask questions in the chat if you don't want if you don't have a microphone or something. I will then transfer your questions. And so thank you very much for being here. And whenever you're ready, you can start.
Okay. Thank you, Justin. Okay. So, good afternoon. First of all, I would like to thank the organizer for this kind invitation. So, in particular, Justin. And I take this opportunity to share with you some results of recent and ongoing collaboration with Professor Vrigerts and his co-worker Blaž Udobivnik from the Institute of Continuum Mechanics in Hannover at Leibniz Universitat. The focus is on virtual element method, in particular serendipity virtual element formulation to model finite strain problems involving compressible and incompressible materials. This is a brief outline. I start explaining the idea behind the work and so the objectives we wanted to pursue. Then I will introduce. I will get to the very heart of the work, that is the virtual element method. I will introduce this method starting from the basic ideas, and then I will move to second order elements and specifically serendipity elements. I will frame this virtual element in application for nonlinear elasticity problems, and I will conclude the presentation showing some examples that highlight the capabilities of the proposed methods. We want mainly to test the effectiveness of the very recent virtual element formulation in modeling problems restricted at the moment to 2D cases, considering compressible and incompressible hyperelastic materials undergoing large strains. The virtual element method is an advanced discretization scheme, an alternative to finite element method that can be defined as a generalization of classical finite element method. So the idea is to treat a problem that is well established in the continuum mechanics, but exploring a new numerical tool that is very promising, that is providing extremely efficient both for its mathematical basis and for its flexibility in dealing with very general geometries, very distorted elements, and also hanging nodes, and you will see also collapsing nodes. The VEM, this method, was firstly proposed 8 years ago by Franco Brezzi, that is a very famous mathematician from Pavia, and his co-workers. And here I show you some seminal papers that are mostly devoted to Poisson equations in 2D and problems with small strain elasticities. Afterwards, The method has attracted the attention, especially of engineers, for versatile applications, and so there are publications, more recent publications, ranging from linear elasticity, also in 3D, damage, crack propagation, contact mechanics, multi-field problems, also homogenization, both adopting computational and asymptotic approaches, dynamical problems, and also nonlinear elasticity problems. The main features of the approach are related to its high flexibility. Differently from finite element method, it is possible to use element with totally arbitrary shape. You can use a convex, concave, and irregular elements. Arbitrary number of nodes in the elements, and the formulation is conceived so that the degrees of freedom are known only at the boundary. And this circumstance is very useful to easily couple also virtual element with finite element. Here there is, you can see a mesh with very imaginative animal geometry, animal shape elements. So each eagle, each horse is one element, each snake is one element, and this is a mesh that was adopted to just to show the flexibility of the method, to adopted to model a crack propagation problem. Here there is a brief, surely incomplete overview of possible application explored so far that range from in this case, scalar damage models, contact problems, computational homogenization, 3D thermomechanical problems, also computational homogenization for 3D polycrystals, and also problems involving phase field and element splitting. Before going into the details of the specific contribution related to serendipity virtual element methods, I would like to set a little bit the scene and establish the broad outline of the method. So let's start with a classical continuum mechanics frame. As a way of example, we restrict our attention to 2D continuum bodies in finite elasticity. And here I recall the classical kinematics relations, equilibrium relation, and to close the set of equations, also constitutive relations. Now, if you want to discretize this problem, let's see what we would do classically using standard finite element approach. We first would consider the domain partitioned into non-overlapping elements. For example, quadrilateral elements in the most simple case with 4 nodes. In the framework of a displacement-based approach, the displacements, so the primal variables of the problem, the exact displacements, are approximated by a discrete solution, the ansatz, that is defined within the entire domain through the shape functions that are explicitly defined for each node x of the domain. Each material point of the domain. As you well known, this approximation is plugged into the weak form of the linear momentum, in this case in the initial configuration. Here the divergence theorem has been already exploited, and eta is a variation, a virtual variation. And after standard algebraic manipulation, it is possible to construct the stiffness matrix, the residual vector, and to solve the nodal displacements. Using an isoparametric mapping, the key idea is that one should move from the physical element space, where possibly distorted elements are considered, into the parent element space, where all the integrations are performed, resorting to numerical integration scheme. One key point of the method is that the Jacobian of the transformation has to fulfill some specific requirements so that some limitation in the mesh geometry arise. The most important is related to the fact that only convex elements are feasible in this approach. So the key point of the well-known and well-established finite element method is the fixed number of nodes and the fact that there are some limitation in the mesh geometry. So there are issues related to very distorted meshes. Moving now to VEM, to virtual element method. Here you can see the same geometry now discretized with elements that are characterized by general shape and general number of nodes. The main difference in this case is that the discrete approximate solution is no longer explicitly given in each material point of the domain. And this is why the method is called virtual. But this ansatz, so this approximate solution, is additively split into a polynomial projection part that is called consistency term, that is explicitly evaluated in the element, and a reminder that play the role of the error between the discrete approximate solution and its polynomial approximation. The idea is that if we only consider the consistency term, the potential density can be formulated in terms of suitable polynomial function. And these, anyway, lead to a rank deficient structure, so that it is necessary to somehow account also for the reminder part in order to add a stabilization term to the formulation. Here there is an example of the difference arising between for a generic element with a generic shape. So the orange contour plot is related to the UP, so to the polynomial space that is effectively defined all over the element, while the UH is explicitly known only along the boundary, while it is never evaluated within the element. And somehow we can account for these two parts. I will explain in the next slide. The main difference with respect to finite element is that it is possible to work directly in the physical space of the element, so without moving to parental space. And it is possible to deal with very irregular shape, also accounting for convex and concave elements. And it is possible to deal with arbitrary number of nodes. This is just to give you a general idea of the method. With this in mind, we can now move to the main part of this talk. As I said, we want to model large strain problems, both considering compressible materials, and in this case, we will use in the example neo-Euclidean strain energy, a neo-Euclidean strain energy function with lambda and mu, the Lamé constants. And also incompressible material behavior. In that case, we will deal with three different constitutive models. Now, Euclidean strain energy function that are here expressed in terms of the strain energy function. So a neo-Euclidean model, a Mooney-Rivlin type model, and a three-parameter Ogden type model. The potential energy function in two cases are here shown. In the case of incompressible materials, the difference is related to an additional term that is the incompressibility constraint that has to be fulfilled. Let us turn now to the discretized problem. So imagine that the domain omega is partitioned into non-overlapping elements. In this case, we can use polygonal elements with general shape. And we define in this on omega, in this domain, V as the space of the ansatz, the discrete space of the test functions. In particular, we are interested in virtual elements characterized by a quadratic projection, so in which the polynomial part explicitly evaluated is considered quadratic polynomials. So in this frame, the test functions never explicitly evaluated all over the element will comprise continuous function that restricted to a generic element include, sorry, there is an extra S, but can be larger than quadratic function. In particular, we assume that along the boundaries, these functions are exactly second-order polynomials, while in the interior domain they are not explicitly known. Let us, here there is a schematic of a generic second-order element. You can see that it can be characterized by a general shape, and over each edge there are nodes that are vertices nodes and also internal node, since we need to define second-order polynomials exactly over the boundaries. Besides the nodal degrees of freedom, a second-order virtual element method account also for an additional, in general, for an additional internal degree of freedom that is defined as first-order moment. This degree of freedom is defined as the integral over the virtual element of the test function U. The discrete test function, as we have already seen, is split and is defined as the superposition of a projection, UP, that is a properly conceived quadratic polynomial, and a remainder. This quadratic polynomial is defined in terms of 12 coefficients in 2D. And now, somehow, we have to link these coefficients to the nodal displacements of this virtual element. So in each virtual element, there are 12 coefficients, irrespective of the shape and of the number of nodes of this virtual element. To do so, to identify these coefficients, these 12 coefficients, the idea is to fulfill this equation that is in average, that states that in average over the virtual element domain, there is an orthogonality condition between the gradient of a second-order polynomial, that is a polynomial of the same order of UP, and the gradient of the remainder. So we are assuming that these two spaces, so the space of a second-order polynomial and the space of the remainder, have zero intersection. After some manipulation, this equation considering separately, so we exploit the scalar product and we obtain two terms. Considering separately two terms, we obtain these two expressions, and exploiting the divergence theorem, we can end up with these equations. In the first term, there are only terms depending on the polynomials, while in the second term, also a term depending on the ansatz u is considered. These integrals, I will not go into details, but these integrals can be solved, in particular the integrals involved in these equations can be solved resorting to Gauss-Lobatto quadrature rules along the edges. In particular, these equations, defining these terms with the name I put here. These equations can be further manipulated, I mean these two equations, and exploiting the automatic differentiation techniques available in ACE-Gen, it is possible to define to obtain this expression that is a system of 10 equations in the 12 unknowns coefficients of A. So we need to add two additional equations that are obtained that are imposed in this last line to univocally determine the 12 coefficients. The equations, the requirement, the extra requirements are that over each element, the mean value of the projected displacement is equal to the mean value of the discrete approximation solution in terms of displacement. By combining the set of 10 equations and the set of 2 equations, it is possible to obtain a final system of 12 equations in 12 unknowns, and it is possible to identify, to obtain the coefficients A. You can see that B2, so the term that is the last term involved here, explicitly depend on the internal moment. That is this internal degree of freedom usually appearing in a second order virtual element. Now we want to do something more. So we want to consider the so-called serendipity virtual element formulation. Here there are some referential works. So the idea in this formulation is that it is possible to get rid of the internal moment, so of this internal degree of freedom. And so the name is borrowed by the finite element literature, because in finite element, the serendipity virtual elements are 8-node elements obtained by eliminating the internal node of a 9-node element. So this is why the name serendipity, because it's a second order element without internal moment. So we want to, I say, to get rid of this internal moment that is defined as the integral of the ansatz u. To do so, following this paper by Beirao Brezzi from 2018, the idea is that it is possible to replace M by a properly defined expression that explicitly depends on D, where D are the nodal degrees of freedom. So it is possible to approximate M as a function of the only degrees of freedom that are defined along the boundary of the element, the boundaries of the element. So the idea is that this moment can be defined as the integral. So the function, so the u can be approximated by a polynomial. Also in this case, a second-order polynomial whose coefficient C are unknowns. To identify the coefficients C, it is imposed the fulfillment of this Euclidean scalar product. As I said, the details are contained in this seminal paper and also in the paper in the paper we wrote with Professor Briggs that I will show you at the end. In this way, we can deal with an element in which the degrees of freedom are only the blue and the red, because we eliminated the green, since we express the green degree of freedom as a function of the others. At this point, we can rewrite the potential energy by using the displacement split. So by considering separately the projection and the remainder. And here there is the expression where we already exploited the summing up over all the element contributions. So the first term is called the consistency term. If we only reduced our calculation to this part, we would obtain rank deficiencies in elements with more than 3 vertices. This is why the second part is required to stabilize the formulation. Considering the first part only depending on the projection, in this case of finite deformation, the first integral, differently from what happens for small strains, the first integral cannot be shifted to boundary integrals, and so we have to numerically integrate over the element area this term that only depends on explicitly known polynomial functions. Considering the second part, the stabilization part, we follow different approaches, in particular 2 approaches. The first one is called nonlinear stabilization procedure that was firstly proposed by Professor Vriegerts in a previous work. The idea is that the stabilization contribution in the potential energy can be in turn, that depends on the remainder of the displacement, can be in turn split in 2 separate contributions, one depending only on u, and the second one depending only on the projection displacement. U hat is a modified energy, strain energy, that is defined, that is related to the one of the consistency term by a stabilization parameter beta that can be optimized. The second part of this expression can be treated as the same way as the consistency term, since only appear in it the projection P, UP, while for the first part a different treatment is required. This part is more problematic. So the idea is that to evaluate this contribution that depends on U, we can embed in the virtual element a mesh of triangles that share the nodes with the virtual element. And so the UA can be evaluated by numerically integrated over the triangles. We propose two different strategies for this nonlinear stabilization procedure. A first possibility is to consider embedded T1 triangles. And the second possibility is to consider instead embedded T2 triangles with additional internal nodes that have to be added. The second strategy is for the stabilization is the so-called discrete bilinear form that was introduced by Beirao in a paper in 2013 and then often used in different contributions. So the idea is that this function is approximated by this expression. So a bilinear form including the difference between the U evaluated in the nodes of the element and UP evaluated in the same node. Concerning gamma is a stabilization parameter, and we consider two possibilities. So in a first case, gamma is equal to the trace of the constitutive tensor that can be, for this neo-Euclidean type model, evaluated analytically, while gamma 2, so a second possible stabilization parameter, is related to the trace of the stiffness matrix numerically evaluated in the element. So I first show you, no, sorry, there is the last part. The global equilibrium is achieved by minimizing the potential energy. And using a standard Newton-Raphson algorithm, we can define the residual vector, the stiffness matrix, the tangent matrix. And so these two terms can be additively split, has already done for the displacement, in two parts. A part, this is for the residual and this is for the stiffness matrix, part that is related to the consistency term and that is obtained by exploiting these the differentiation of the strain energy function with respect to the displacement field, and a second part that is related to the stability, that is called the stabilization part. Is the same thing, but starting from U stabilized and not U consistent. Analogously, by differentiating the residuals with respect to displacement field, it is possible to attain the two contributions for the consistency and the stabilization part of the stiffness matrix. All this is done exploiting the symbolic tool ACE-GEN, ACE-FEM that enables automatic differentiation schemes. Let's now turn to some examples related to compressible materials. Then I will show instead the problem related to incompressible materials. So the first example is a Cook membrane test. Here the geometry is depicted. So the trapezoidal plate is clamped at the left side, while there is a constant distributed load, vertical load applied on the right edge. We want to test the performances. We assume neo-Euclidean constitutive model for this specimen. We want to test the performances of both Voronoi meshes and regular meshes for this example. Here there is a deformed shape using a quite coarse Voronoi mesh. And first of all, we perform a convergence study using, so in this case for regular meshes and for Voronoi meshes. The idea is to use a uniform mesh refinement so that each subsequent mesh can be exactly contained in the previous one. And turning to Voronoi meshes, the idea is to consider the equal number, a mesh that has the equal number of elements than the corresponding regular one. We here, for regular meshes, compare the performance of 8 nodes virtual serendipity virtual elements using the 4 different stabilization schemes, so with T1 triangles, T2 triangles, and bilinear form with gamma 1 or gamma 2 stabilization parameters. We compare this with standard finite element, Q2 elements with 9 nodes, and serendipity finite element with 8 nodes, and also virtual element with first order polynomial scheme, so a low order virtual element is compared. As you can see, for the regular meshes, the best performances between our elements are provided by the VMS-T2, so the one with T2 embedded triangles, and the performance are better than the corresponding Q2S element, so the corresponding serendipity finite element, and a little worse, but just for the coarsest mesh, than Q2 element. Anyway, in all cases, a very fast convergence is obtained. Also for Voronoi mesh, where a very robust behavior and fast convergence is observed. A further study for evaluating the accuracy of the numerical solution concerned the evaluation of this norm, that is a L2 type global error measure that is obtained by extending to virtual element what is done for a finite element. The idea is to consider all over the domain the difference between the actual displacement obtained with the virtual element solution and the displacement obtained with an overkill finite element solution that is an extremely finite element mesh. In this case, both for regular meshes and for Voronoi meshes, it is possible to see that the VEM formulation leads to an optimal convergence rate that is 3. So in these plots, we are plotting this error norm with respect to the average mesh size. We expect to have as optimal convergence rate a value of 3 in case of second order element, and this is the case. So these results confirm the optimal convergence rate of the proposed approach. The second example is a punch test, where a rectangular specimen undergoing a vertical load over half of the upper part is applied. Sorry, how long?
It's okay. You still have some time.
How much? Because I forgot to put the time.
5 minutes. 5 minutes.
Okay. Okay. Perfect. Okay. And this is another example. So I will go faster on these. Also for this example, we can see, we can confirm the optimal convergence rate of this formulation. The last example for compressible material is a square plate with a central hole. Also in this case, the formulation exhibit very stable, very robust and fast convergence properties. I will briefly introduce just a few ideas of what we have done on incompressible materials. So the main difference is, as I said before, this incompressibility constraint that can be enforced using a Lagrangian multiplier formulation, where the multiplier P can be physically seen as pressures. The idea in this work is to use a Taylor-Wood type mixed formulation for virtual elements, in which the displacements present quadratic serendipity ansatz, while for pressures, different possibilities are explored. In particular, we assume, for example, discontinuous constant pressure field or continuous constant pressure field, or even we assume a possible Taylor series expansion of the pressure, where xb is the centroid of the element, assuming linear ansatz or constant ansatz of the pressure along the boundaries. I will not give detail on this. If you are interested, then I can show you a reference paper. And in this case, we have to deal with a mixed potential where both displacement and pressure appear. For the consistency term, we have surely to deal with also the stabilization of this method, and we have to stabilize both displacement and pressure this time. For the stabilization of the displacement, we adopt a discrete bilinear form, as we have done for the compressible case, while for the pressure, we adopt a stabilization that is a mixed stabilization. Also for this, I don't have time to go in detail. Some results, maybe I will focus only on a few things. So we compare the different responses of using discontinuous, continuous, Taylor series, linear, Taylor series expansion, constant approximation for the pressures. And what we observe is that the best performances are related to the element with Taylor series expansion and of the pressure and the linear expansion along the element boundaries, while the one with constant expansion along the boundaries exhibit checkerboard modes for the pressure. That means that this formulation is not stable, and them as in this formulation instead with linear expansion along the edges is very stable also for Voronoi meshes. And okay, these are maybe this is the last example I show. We consider a rubber bashing with a Mooney-Rivlin constitutive model. So the inner frame is rigidly displaced downward up to this final deformed shape. We compare in terms of global curves the response of different elements, and also in this case what we can say is that the best, so all the elements are behave quite nicely, but the best performances are delivered by the element with Taylor series expansion and linear approximation along the boundaries. Okay, that was the last example, but no problem. I can go at the end. The results presented in this presentation are from these two papers, one from 2019, Serendipity Virtual Element Method, while now, very recently, we extended the formulation to the incompressible case. Okay, I think I can stop now. And if you want to ask me something, I will be happy.
Thank you very much. Thank you very much for this.